Welcome to this explainer. Today, we're going to trace the incredibly chaotic, violently explosive, and ultimately beautiful 4.6 billion-year cosmic journey of our home planet.
So let's just dive right into this massive mystery. How exactly did a hostile, entirely lifeless ball of magma manage to transform into the vibrant, blue, life-sustaining world that we live on today? I mean, it is quite literally a story of violent collisions, immense luck, and absolute cosmic perfection.
Section 1. Birth of the Sun. Out of the cosmic darkness.
We have to begin our journey chronologically, way out in deep, quiet space. Right around 6 billion years ago, heavy elements were just starting to form, and by 4.6 billion years ago, a really dark cloud of hydrogen and helium, what we call the solar nebula, was just peacefully drifting along. But then, we get the inciting incident. A dying star's supernova sent these massive shockwaves ripping through the cloud, and that caused the entire nebula to collapse inward into a flat, rapidly rotating disk.
Now get this, because the sheer scale here is just mind-boggling. As that nebula collapsed, nuclear fusion ignited at a blazing 15 million degrees Celsius, creating our sun. And our hungry newborn star? It consumed a massive 99.8% of all the mass in the newly forming solar system. Just almost the entire thing.
Section 2. The process of accretion, from stardust to planets. Okay, so you might be wondering what happened to that leftover 0.2% of dust and gas just swirling around the newborn sun. Well, it went through a process called accretion. This idea was proposed by a Soviet astronomer named Viktor Safronov back in 1969. And accretion is basically just the coming together and cohesion of scattered matter, driven by gravity to form solid, larger planetary bodies.
And this planetary building process happened literally step by step. It's kind of crazy to think about, but it started with microscopic dust particles just sticking together through simple static cling. Over time, those grew into small clusters, which eventually expanded into kilometer-wide chunks of rock called planetismals. Finally, gravity took over completely, and over tens of millions of years, it formed these massive moon-sized protoplanets.
Now, how do we actually know all this? Well, scientists can confidently prove it by looking at ancient meteorites that crash into Earth. These rocks act like little time capsules containing chondrules, which is literally primordial dust from before the planets even formed. And here's the coolest part. By using radiometric dating, scientists figured out that the radioactive uranium found here on Earth is actually 6 billion years old. So, yeah, it actually predates our entire solar system and was forged in some ancient distant supernova.
Section 3. Earth's hellish Hadean Eon, a crucible of fire and ice. Next up, we have to drag our newly formed Earth through a literal hellscape. It's called the Hadean Eon, named after Hades, the Greek god of the underworld, and it presents this incredible contradiction. On one hand, you had constant protoplanet collisions turning the early Earth into a toxic, boiling sea of endless fiery magma, just totally hostile. But paradoxically, this violently chaotic era is surprisingly what delivered our life-giving water. All those colliding comets and asteroids were carrying vital ice crystals and liquid water directly to the Earth's surface.
Section 4. Shaping the Earth's layers, the Archean Eon, and differentiation. So as those constant collisions finally started to slow down between 4 and 2.5 billion years ago, Earth entered the Archean Eon. This brought about a massive internal stabilization. Think about how water makes its way down through sand. A process called differentiation basically pulled elements apart based entirely on their density. Intense gravity pulled the heavy, dense elements, like iron and nickel, way down to the Earth's center to form the core. Meanwhile, the lighter stuff, like oxygen, silicon, and aluminum, kind of floated to the top to form the crust. Actually, oxygen was so abundant back then, it made up a whopping 46% of the early crust's mass.
Now, I know your middle school science class probably taught you about 3 super simple layers, crust, mantle, core. But deep geology reveals there are actually 5 distinct physical layers based on their properties. It ranges all the way from the brittle tectonic plates of the lithosphere on the outside, down through the lubricating asthenosphere, into the high-pressure mesospheric mantle, down again into the liquid, churning iron of the outer core, and finally into the intensely pressurized inner core.
Deep inside all of that, extreme pressure keeps that inner core entirely solid. And fun fact, it's actually growing by about 1 millimeter a year as the outer core cools down. Meanwhile, the constant radioactive decay of elements like uranium and thorium inside that massive 3,000-kilometer thick mantle layer is driving immense internal heat. We're talking up to 6,000 degrees Celsius. But all of that intense internal heat serves an absolutely vital, life-saving purpose. That churning liquid iron in the outer core, it acts as a massive electrical dynamo. It generates this powerful magnetic field that firmly protects our fragile atmosphere from getting completely stripped away by deadly solar winds. Without it, we literally wouldn't be here.
Section 5. The Giant Impact Hypothesis. A violent collision creates the moon.
But wait, our chronological journey is missing a pretty crucial character in the night sky, right? How exactly did Earth get its moon? For decades, scientists puzzled over this exact question, and it led to a ton of highly debated theories.
Historically, there were a few famous ones that got tossed out. The capture theory suggested Earth's gravity had just, snagged a passing object. The co-formation theory guessed that they formed side by side from the exact same dust cloud. And the fission theory actually imagined early Earth was spinning so incredibly fast that a chunk of it just broke off. They were all really popular ideas at the time, but ultimately, they were rejected for a far more violent truth.
Today, the giant impact hypothesis tells us that the moon is actually a piece of Earth's own debris. It happened when a literal Mars-sized protoplanet named Theia horrifically crashed into Earth very early in the solar system's history. This impact was so unimaginably severe that it actually fused their cores together, blasting a ridiculous amount of debris up into orbit. And over time, all that debris coalesced into our moon.
The proof we have for this is absolutely wild. NASA's Apollo soil samples prove that the moon shares Earth's exact oxygen isotopes, like a perfect match. Most of Theia's heavy metals fused into the Earth, which is why the moon is left with a tiny 1.6% iron core. But crucially, this collision knocked Earth right off its axis, giving us a 23.5-degree rotational tilt. And that exact tilt, that is what gives us our changing climatic seasons. Plus, the gravitational pull of the newly formed moon created our oceanic tides, a daily rhythm that eventually encouraged early marine life to adapt and crawl onto land.
Section 6. The Recipe for Life. The Ultimate Cosmic Balancing Act.
So, finally, the cosmic chaos started to settle down, leading us to this incredibly precise balancing act required for our existence. As that toxic, volcanic early atmosphere started to cool, water vapor condensed and literally rained down for millions of years to form our massive oceans. And those oceans did something heroic. They absorbed the extreme heat and the toxic carbon dioxide levels in the air, which finally paved the way for life-sustaining oxygen to slowly rise up.
Talk about winning the cosmic lottery, right? We exist today purely because of an incredibly lucky combination of Goldilocks preconditions. We happen to be the absolute perfect distance from the sun for liquid water. We are the exact planetary size needed for a gravitational pull strong enough to hold onto a life-giving atmosphere. Our core acts as this vital magnetic shield against deadly radiation, and we had perfectly balanced volcanic activity creating just enough of a greenhouse effect to keep us warm, successfully avoiding the completely frozen fate of Mars or the boiling toxic fate of Venus.
So considering the sheer improbability, the immense cosmic luck, and the billions of years of chaotic, violent progression required just to create this perfect recipe for life, how will we choose to protect our incredibly rare, beautiful planet moving forward? It is a genuine miracle that we are here at all, and it's a responsibility we definitely shouldn't ignore. Thanks for joining me on this explainer. I hope you found this journey as mind-blowing as I did.